Dear students, today we are going to discuss about state variable analysis. In this case, we will go through state equations and state space representation of the continuous time systems. Let us see the state space formulation. A set of variables which describes the system at any time instant are called state variables. So, for a control system at a particular time instant, we can use state variable to represent that systems. So, state variables are a set of variables which describes the system at any instant of time. See, here there is a control system which is shown in figure. In this case, there are different inputs, there are outputs, also there are number of state variables. So, in the case of state variable formulation of the system consists of m inputs. Which are the inputs? u1 of t to um of t are the inputs. And p outputs. What are the outputs? y1 of t to yp of t. And also there are n number of state variables, that is x1 of t to xn of t. And this is the state model of the system. So, the state space representation of the system is visualized like this. So, state variables are this one. Input variables are u1 of t to um of t. Output variables are y1 of t to yp of t. So, we can represent u is the input, y is the output and x is the state variables. So, this is the control system. So, this is the state space representation of the system. So, the different variables may be represented by the vector form as input variables are u. So, we can represent it by a column matrix u1 of t, u2 of t, um of t. Output vectors can be represented by y of t equal to y1 of t to yp of t, which is also a column matrix. This is a 1 by p column matrix. This is a 1 by, this is n by, this is p by 1 column matrix and this is m by 1 column matrix. And next state variable vector is x of t, which is x1 of t to xn of t, which is n by 1 column matrix, that is n rows and 1 column, that is its meaning. So, these are represented by column matrix. Okay. So, next we can formulate the state equations corresponding to the control system. So, the state variable representation can be changed in the form of n number of first order differential equations. See, we know that there are state variables x1 to etc. up to xn, input as u1 to um. So, the function of these state variables and input are the first order differential form of x1. So, the state variable representation can be arranged in the form of n differential equations. So, first differential equation is dx1 by dt, that is represented by x1 dot, and that is a function of a state variable and input, that is its meaning, that is f1 of x1 to xn and u1 to um. So, next state variable is x2. So, its differential equation is dx2 by dt, that is x2 data, that can be represented by the function of state variable x1 to xn and input u1 to um. Similarly, we can write nth state variable dxn by dt, which is xn dot, that is a function of fn of x1 to xn and u1 of um. So, these functions will be different. So, the function of state variable and input will give the first order differential equation for the first state variable. Okay. So, similarly, we can formulate different state differential equations for state variable. Okay. Here we can say, we can define an input space. Actually, input space means that it is a set of all possible values of input vector u of t. Similarly, output space is set of all possible values of output vector y of t. And state space is the set of all possible values of state vector x of t. That is simple definitions for input space, output space and state space. So, it represents all possible values of the input vector or output vector or state vector. So, the differential equation, we have defined a differential equation here. We can generalize this equation as x dot of t. Okay, see, this is left side is x dot of t. That is equal to function of x of t and function of u of t. Okay. So, we can represent the function of x of t comma u of t. So, that is the differential equation corresponding to this in terms of vector notation, that is x dot of t equal to f of x of t and u of t. That is the first order differential equation corresponding to the state variable can be represented by the function of state variable and input. Okay. Next, let us see the state model of linear system. Usually, the state model consisting of state equation and output equation. So, it is an important thing, that is you should remember this, that is state model consisting of state equation and output equations. So, let us see what is state equation, then we can go to the output equation. First of all, we will go to state equation. So, state equation is, what is state equation? This is the function of state variable and input variable. Okay. So, state equation is the function of state variable and input. So, we are first referring the LTI system, that is linear time invariant system, and the first order derivative of the state variable can be represented by the matrix form. So, that is, see, this is x dot of t. Similarly, there will be have n x values, right? See, here there are n variables. Okay. So, we can represent it in the matrix form as left side. See, we here this is x dot of t, and that is function of x of t and u of t. So, we can represent it in the matrix form as x1 dot x2 dot x3 dot x up to xn dot. That is equal to function of x of t and u of t. So, that function of x of t can be represented as a11, a12, a1n. Similarly, a21, a22 etc. up to a2n. Similarly, an1, an2 etc. up to ann. And next term is x1 of x2, x3 etc. up to xn. So, this is the function of state variable. Okay. Plus, next is the function of input. That is, input is u1, u2, u3 etc. up to um, and the function can be represented as b11, b12 etc. up to b1n, b21, b22 etc. up to b2m, like that bn1, bn2 etc. up to bnm. So, this is the representation which represents the this equation. Okay, x dot of t equal to f of x of t into u of t. That is what is called state equation. So, state equation can be represented in the matrix form like this. Okay. So, remember this relation. This is similar to this one. Okay. This one. Okay. So, the matrix, let us see what is those matrix. The matrix, this is equation 4, and matrix, in the matrix form we can represent it as x dot of t equal to a into x of t plus b into u of t. This is a, this is x of t, this is b, and this is u of t. Okay. So, x of t, what is x of t? It is the state variable matrix. Okay. So, we can represent x of t as a state vector. This is state vector having order n by 1, right? Similarly, next is u of t. U of t is this one. U of t is the input vector and its order is m by 1. Similarly, there is another matrix A. That matrix is called system matrix of order. What is its order? N by n. Okay. Its order is n by n. That is called a system matrix. And next is the input vector is multiplied with this one. So, we can call it as input matrix and its order is n by m. Okay. So, the A is the system matrix. Its order is n by n. B is the input matrix. Its order is n by m. And state vector matrix is n by 1 and the input vector matrix of m by 1. So, this is an important relation. You should remember this relation. Okay. So, this represents the state equation. Okay. Next, so we have written that x of t equal to a into x of t plus b into u of t, which is called the state equation of the linear time invariant system. Okay. Next, we have to go to the output equations. We know that here it is defined that a state model consisting of state equation and output equation. State equation we have obtained here. This is the state equation. And next we have to derive output equations, and the output of at any time are the functions of state variables and input. See, like the previous relation, the state variable is the function of state variable, and first order differential equation for the state variable is a function of state variable and input. Similarly, we can say that output is also a function of output vector is also a function of state variable and input variable. So, the matrix form we can represent as C y of t equal to f of x of t into u of t, s of t comma u of t. So, here y of t is y1, y2 etc. up to yp, because we are representing the control system as n. You can see here this is m having m inputs and p outputs. So, we are writing the output up to yp. So, y1, y2, y3 etc. up to yp will be equal to what is function of x of t and u of t. X of t is x1, x2 etc. up to xn, u of t is u1, u2 etc. up to um. Next, function of x of t and u of t can be represented by the matrix C11, C12 etc. up to C1n. Similarly, it will goes to CP1, CP2 etc. up to CPN, and this matrix is called, this C matrix is called output matrix of order, what is its order? Output matrix of order P by n, and this is x of t, that is state vector of order n by 1, that is we have seen the previous slide, that is this is state vector of order n by 1, and next matrix is D matrix, which is d11, d12 etc. up to d1m. Similarly it will goes to dp1 etc. up to dpm, and its order is equal to p by m. Okay, p by m is its order is p by n, and this is u1 ut etc. are called input vector. See, state vector and input vector are same in the previous case, and its order is n by 1 and m by 1. Here also state vector and input vector is order n by 1 and m by 1. So this is the output equations or output functions or output vector for a linear time invariant system. You should remember this thing also, and here you should remember the orders of this equation. This is y is equal, this is similar to y is equal to c into x of t plus d into u of t. X of t is in state vector, u of t is the input vector, its order is n by 1, its order is m by 1, and similarly c is output matrix of order, this is output matrix, its order is equal to p by n, and this is transition matrix, D is called a transition matrix, its order is p by m. So that you should remember. In the previous case, this is input state vector, sorry, this is state vector, and this is input vector, its order is n by 1, its order is m by 1, and this is what is, A is called system matrix and B is called input matrix. Okay, input matrix order is n by m. Here also C is output matrix and this is transition matrix. This is input system matrix and this is input matrix. Okay, so this is the, so now we have two equations, that is x of t in terms of x of t and u of t, y of t in terms of x of t and u of t. So these two equations are called, this equation is called output equations. So the state model is obtained from the state equations and output equations. State equation is x dot of t equal to a into x of t plus b into u of t, and similar output equation is y of t equal to c into x of t plus d into u of t. You should know what is a, what is b, what is c and what is d. Okay, so the state model of the system consists of state equation and output equations. Okay, next we will go to the state diagram. So state diagram represents the pictorial representation of the state model. See, state model is this one. Okay, so this is the state model, these two constitute the state model, and it can be represented pictorially, and that representation is called a state diagram. So we can use two methods, such as in order to represent a system, we can use pictorially represent a system by using block diagram method, or in the case of, or by using the signal flow graph method. And here, for representing the state diagram in terms of block diagram or signal flow graph, we need equations representing the system. Okay, so in order to get the time domain state diagram, we need a differential equation corresponding to the system. So similarly, in the case of S domain, state diagram is obtained from the transfer function of the system. In the time domain, we are obtaining the state diagram from the differential equation corresponding to the system, and in the case of S domain, the state diagram is obtained from the transfer function of the system. Okay, so this is the important thing. So in order to solve the problems, you should know, if you are giving the differential equation, you can represent it in a state diagram. Similarly, if you are given by a S domain equation, then you can that is transfer function, you can also find the state diagram. So state diagram mainly consisting of three elements, and these three elements are scalar, adder and integrator. Scalar means which is used to multiply a signal by a constant. You might have gone through the scalar quantity when we have discussed about the block diagram representation. And so scalar in that block diagram representation is used to multiply a signal by a constant, and adder is used to add two or more signals, that we have gone through in the block diagram representation. And integrator means which is used to integrate the signal. Let us see. In the case of block diagram, time domain and S domain cases, scalar is represented by the constant number which is multiplying the signal. So x of t is input signal, so output is a into x of t. Similarly, adder is used to add two signals. Here x1 of t and x2 of t are added to give x1 of t plus x2 of t. Integrator is used to integrate the signal. Suppose if you are giving the first derivative of the signal, so to get the input state variable, we are integrating it. So integrator, its symbol is like this. So we can use this integrator in the case of block diagram representation, and whenever we are integrating it, we will get a signal corresponding to the integrated value, sometimes there may be initial conditions, so we have to add those initial conditions along with the integrated signal. So the adder is used after the integrator in order to add the initial conditions. So the output will be integral of this function x dot of t plus initial condition is x of 0. Okay. Similarly, in the case of S domain, we are instead of t domain equation, we will be using S domain values. So that is, instead of x of t, we are using x of s. A into x of t gives a into x of s. And similarly, if we are using adder, we will be giving input as x1 of s corresponding to x1 of t, corresponding to x2 of t, we are using x2 of s, and output will be x1 of s plus x2 of s. That is, function is same, but the domain representation is different. Similarly, in the case of integrator, here we are, if we are representing it in the block diagram method, here we are using this symbol, and in the case of S domain representation, we are using 1 by s. That is, x of s is multiplied by 1 by s. That means we are integrating x of s. That is its meaning. When we are using integrator, we have to add initial condition. That is, here initial condition is x of 0 by s. That is added. So we will get at the output x of s by s and x of 0 by s. So these are the two representations or state diagram representations in the case of time domain and S domain. And you may remember this because it is very easy to remember. We have gone through these sessions when we are discussing in the block diagram representation. Okay. So next is the, when we are representing the state diagram in terms of signal flow graph, suppose here in the case of signal flow graph also there are different elements, scalar, adder and integrator. In the time domain case, the scalar is represented by, above the arrow mark, we are representing the scalar quantity A. Here input is x of t and output is A into x of t. Similarly, in the case of adder, we are adding two signals. So the lines will be joined at a particular point. That means it is added here. That is, x1 of t and x2 of t is added here. The scalar is 1. Okay. In the case of integrator, actually we are using the symbol integral. That is, x dot of t is integrated. So to get x of t, so the integrator symbol is shown like this in the arrow mark section. And when we are integrating the signal, sometimes there may be initial values, so we have to add it by using an adder. That is why we are showing it as a line joining of two lines. Okay, that is x of t and x of 0 is obtained here. These all are time domain representation. In the case of S domain, we have to use, instead of x of t, we have to use x of s. Here it is a into x of s. Here x2 of s, x1 of s and x2 of s, and here x1 of s plus x2 of s. Here it is x of s, and integrator is represented by, above the arrow mark, 1 by s. That is the important thing. Here in the time domain we are using integral symbol. In the S domain we are using 1 by s. That is, it is the input signal is multiplied by 1 by s quantity. And when we are integrating the signal, sometimes there may be initial values. So that is why we are representing it as x of 0 by s. So after the integrator we have to use adders. So we are adding it that as x of s by s plus x of 0 by s. So these are the way we are representing a state model, or this is a state diagram representation. Okay. See, here is a block diagram, and how can we convert this block diagram into signal flow graph? You can see here that this B represents the scalar quantity. So first of all, we will represent each of the variables as input is represented by a node, and here also there is another variable, this is represented by a node, and x of t also represented by a node. So first representation, that one, here u of t is represented by a node. Here u of t is the input. Okay. Next variable is x dot of t, that is also represented by a node. Next variable is x of t, that is represented by a node. Next variable is y of t. Okay. First thing is we have to represent each of the variables by a node. Next we can, starting from the first node u of t goes to b and then to adder. Okay, so we will represent by a line, and above that we will represent the scalar value b. So we will get x dot of t here, and we know that from the u of t node d is going outside, so we can represent a d outside, and it will end at where y of t. So we can join here, and the arrow mark is put here, and d value is marked here. Next, we have reached up to this point, x dot of t. What will happen after x dot of t? That will be integrated. So we have to represent a line, and above that we can represent the integral symbol, and it will goes to x of t. So we can represent it. But in the x of t, there is a feedback signal having scalar value a that is fed back to x dot of t. So we can represent it by a backward arrow mark that is having scalar value a. From the x of t, then we will go to y of t and the scalar value is c. So that is represented by c. So this is the conversion that is that is what we are using for converting the block diagram into signal flow graph state model. Okay. Next we can go to the section how we are getting the state model or state diagram from a differential equation. So there are some simple steps. So how can we construct a time domain state diagram? So in the question you will be given by a differential equation. So in the state space modeling, n number of first order differential equations are formed for an nth order system. So in the question you will be given a differential equation. So if there are n differential equations, then what is its meaning is state diagram requires n number of integrators. So state diagram may be either in the block diagram format or in the signal flow graph format. We have to construct a state diagram for a differential equation. Then if there are n differential equation, there will be n integrators, or if there are nth order differential, if it is an nth order differential equation, then there will be n integrators. Okay, so you have to draw n integrators first. So first step to draw the state diagram is to draw n number of integrators. How can you draw the integrator? Integrator symbol is this. Okay, so you can draw n number of integrators. That is the first step. And so there will be an input to the integrator and also there will be an output to the integrator. Next we can give the input to the integrator. So input of the integrator is first derivative of the state variable and output of the integrator is the state variable. See here, input is first derivative of the state variable x of t, that is x dot of t is the input, and output is state variable itself, that is x of t. So we can mark this input and output to that integrator. And next step is representing the first derivative of the state variable. Here we are having first derivative x dot of t. Okay, so where will it come from? That will be coming from the previous block. So next step is, second step is representing the first derivative of the state variable. Okay, the first derivative of the state variable is represented by x dot of t. Okay, x dot of t, we have the equation that is x dot of t is equal to, see in the previous case we have x dot of t is equal to a into x of t plus b into u of t, or x dot of t is a function of, you can see x dot of t is a function of x of t and u of t, right? So that is obtained from either from the previous state variable or obtained from the input conditions. So in the next step, x dot of t is equal to f into x of t comma u of t. So from the state equation we will get the relation of x dot of t. So by using the state equations we can find x dot of t. So here x dot of t value will be obtained from the state equations, and we can mark the block diagram representation, or we can draw the block diagram corresponding to that state equation. That is the next step. And in the third step, first derivative of the state variable is given as input to the integrator. Okay, so now we have obtained x dot of t. So in the third step, first derivative of the state variable is given as input to the integrator. That is we have done in the first step also. And similarly, input to all integrators can be drawn by considering state equations. And now we have constructed the block diagram for the input section. Next we will also have output equations. From the output side can be drawn from the output equations. That is, output equation is y of t equal to c into x of t plus d into u of t. From that output equation we can draw the state variable, and input are multiplied by appropriate scalars and then added to get the output. So this output is obtained by adding the state variable which is multiplied by suitable scalars and also from the input. So input is going here. So this from this output equation is obtained. From the output equation we can draw the output variable. Okay, so the thing will be clear, or the session will be clear when you are going to the problem. Okay, so here first we will discuss about the electrical system state diagram representation. In the case of electrical system, you know that what are the components of electrical system: resistors, capacitors and inductors. So for finding the state space representation for the electrical system, first of all we know that the basic model is obtained by using R, L and C, right? So we will be having a network that is including resistor, inductor and capacitor. So first of all you have to indicate the state variables. For that usually we are assuming lesser number of state variables. And how will we get these state variables? So the state variables will be the voltages and currents in the energy storage element. Suppose if we are having inductor and capacitor, then the voltages and currents of that inductor and capacitor will be represented by the state variable. So we have to choose a minimal number of state variables, and once we choose the state variables, we can write the KVL or KCL equation corresponding to the particular network. That is depends upon depends upon you, because you can apply either KVL or KCL. That depends upon the circuit, and after applying the KVL or KCL, you can represent the corresponding variables by the state variables. Okay. So the physical variables in the differential equations are replaced by state variables, and equations are rearranged as first order differential equations. Also, when we replaces the variables in the network or differential equation by the state variables, you will get the state equation. That is, state equation is in terms of state variables. And input to the systems means the voltage sources and current sources, that is the value of voltage source and current source, and output variables are any voltage or current in the network. Okay, this is a basic consideration that we are adopting in the case of state space representation of the electrical system. So once you are getting an electrical system consisting of R, L and C, first you have to assume a state variable. Usually state variables are the voltage or current across the inductor energy storage elements, that is inductor or capacitor, and output variables maybe either the voltage or current across any part of the network. So this is the state space representation of the electrical system. You know that it consisting of a state equation and a output equations. So next we can do a problem. Thank you.